On the previous slide, we used the z-score table to find probabilities and proportions corresponding to specific z-score values. In most situations, however, it'll be necessary to find probabilities for specific x values. Whenever you start out with raw scores in the problem, you must transform x values into z-scores before you can use the information in the z-score table to find the probability, proportion, or percentage. Again, just as is shown in the example figure on the slide, it's recommended that you draw the distribution and then shade in the proportion of the distribution you want to find. In the problem shown on the slide, you start out with a distribution of IQ scores, and someone has an IQ score of 120. The task is to find the proportion of people who have IQ scores less than 120. Before you can answer that question, you have to transform the raw score of 120 to a z-score, and in this case, as is shown on the slide, the z-score is z equals 1.33. Then you can consult the z-score table, find the z-score of 1.33, and locate the proportion in the body column, column B, to correctly find that the proportion of scores less than z equals 1.33 is a 0.9082. The next example demonstrates the process of finding the probability of selecting a score that is located between two specific values. Although these problems can be solved using the proportions in columns B and C, the body and the tail, they are often easier to solve with the proportions listed in column D. For the graph on the top, the task is to find the proportion of scores between a raw score of 55 and a raw score of 65. We know now that when we start out with raw scores, to use the information in the z-score table, we must transform those raw scores to z-scores. This has been done for us, and the z-scores are on the axis below the top graph. Our task then is to find the proportion of scores, or the probability of a score occurring, or the percentage of scores between a negative 0.30 and 0.70. The notational format is shown on the slide. To solve this problem, we will consult column D and find the mean to z values for both z-scores. Those values are 0.1179 and 0.2580, and then we add them together to calculate the number that represents the entire shaded area. So P equals 0.3759. In the second graph on the lower right, we still use column D to find the mean to z proportions for both z-scores. Z equals 0.70 and z equals 1.70. However, in this situation, because we only want to find the proportion of the shaded area, we will subtract the smaller value from the larger value. Those values are 0.2580 and 0.4554. Thus, 0.4554 minus 0.2580 equals a 0.1974, or 19.7% of the scores are in the shaded area. For this last practice problem, we again start out with a problem scenario that involves raw scores. The scenario is: the U.S. Census Bureau in 2005 reports that Americans spend an average of 24.3 minutes commuting to work each day. Assuming that the distribution of commuting times is normal, with a standard deviation of 10 minutes, how much time do you have to spend commuting each day to be in the highest 10% nationwide? Figure 6.14 on page 167 in your book graphs out the problem and shows the shaded area for which we have to find the correct proportion. Thus, the problem is to find the score that separates the highest 10% of commuting times from the rest, or, put in our notational format, the proportion of scores greater than 1.28, and that actually equals 0.1003. This number should look familiar because we had a problem earlier in this chapter where we were working with these same values. Here, however, we want to actually find a raw score. How much time would you have to spend to be in the top 10% of commuters? We can easily do this by putting the z-score, population mean, and standard deviation into the formula you learned in Chapter 5 to transform z-scores back into raw scores. The formula is shown on the slide. So to be in the highest 10% of commuting times, someone would have to be commuting a minimum of 37.1 minutes each day.